Let the record begin. Come on. Come on. Okay. Now, I don't think this is very useful. As I mentioned yesterday, what I think not good for anymore. I don't. Okay, I don't mention it. Now, this is useful and it makes sense to at least let you know what the loading conditions can do to you. So the next question is, how would we get the maximum positive bending moment? Why maximum positive? Because think about it, this is probably the application of bridge. When you build a bridge, it's not like the very big one beside the Rama 9 bridge. Generally, you would build a simple beam for ease of construction. Generally, say, that's not a simple beam. It's just something we call it a cable stay bridge. Yeah, but somewhere there's a simple beam portion like that. Okay, so now it becomes a simple beam, and a simple beam, we civil engineers generally deal with the gravity load. So we would focus on the positive bending moment, correct? Not the negative one, because I'm not going to push this up like that. I'm just going to push it down by the truckload instead. So when the trucks come in onto the bridge line, what is my maximum positive moment? First question is what? How much? You say probably. So before we think about that, let's narrow down our question from how much to where. Where would the maximum bending moment occur? And where if we need to place all the loads so that we have worst case scenario. Okay, just access the data and all. We have the worst case scenario on our structure. Why do we need to have the worst case scenario? Can you answer me? Exactly. Because it's your job. No matter what you do, as long as you are an engineer, you need to find every possible way that your structure can fail and prevent them from happening. This is success. Yeah. For example, if you're involved with the soil mechanics, want to build the foundation, you need to know every possible way that the soil can destroy your foundation and prevent every one of them from happening. The worst case scenario would be the one that if you prevent, the rest should not occur. So if we can find the largest maximum moment and we design our structure for that, it means that we ensure that our structure will stand. It's a simple idea, right? So now the question is not just where the maximum bending moment is, but where we have to place the load as well. So let us look at this. Now I have a series of layers put on this beam. Now I can represent this load by the total load Q. Okay? So sigma B, right? Total load. Okay. All right. Let us assume that maximum moment occurs underneath the P. If you know one thing that has amazed me in not a very good way in the past years, that when you generally would wonder after you know how to place it, where the maximum moment is occur. Whatever happens about the shear force and bending moment diagram. When you have the maximum moment, what is going to be your shear? 0. So maximum moment always occurs where the shear becomes 0. And if we have a series of point load like this, chances are the shear is going to be 0 in one of underneath one of these loads that we have, right? Because your shear force diagram is going to look like this. Somewhere it's just going to come down, cut the 0 line. So let's say it's this one, P3. Okay, we do this because that's where the shear will definitely be 0 underneath one of the loads. Okay, now let's say it's underneath P3, and now I'm going to write the moment equation. Okay, M3 now will be let's before that, let's write the equation for the reaction first. If the total load is Q and it is at the location X from the left, and now to help clarify this, now we look at this look Q. If this is X, when you take the moment at this point, this becomes L minus X. If L now is the span length. Take moment at B to find RA. This becomes L minus X multiplied by Q divided by L. That's your RA. So here essentially is RA. Okay. Now we take moment at 3. I use the symbol X to locate Q, and then the distance from Q to load P3, I call it S. So this becomes the RA multiplied by the momentum X plus S, and minus P1 multiplied by D1 and P2 multiplied by D2. So this is simple free body diagram of this one. This is RA, this is P1, and this is P2. We take the momentum, okay? So that's why we use P1 multiplied by P1, P2 multiplied by P2. Their respective distance to 0.3. Okay? Now this is your moment. To have M max V must be equal to 0. So what do? Differentiate. Right? We differentiate this equation to try to set it equal to V to get the location of the V max or M max. Here, dm3 by dx. So we differentiate that, and notice that. Sorry, I need to back. The last two terms here doesn't have any x in it, so they definitely drop out because we differentiate the constant, right? No x. So here we have this, but we need to do a little bit more of the differentiation by part, right? It's like u dv plus v du, that kind of thing. Come on, right? You should enjoy it. I can sense your A coming out as soon as I mentioned calculus. So, okay, let's try to. Okay, we differentiate this. So we differentiate the first term, leave the second term, and the second term, leave the first term. So let's skip that. So this is what we have. After that, and rearrange the term. So we have in the end this equal to 0, right? Because we want the maximum moment. We need to set it equal to 0. Q is the summation of your load, can't be 0. L is the length of your beam, can't be 0. So the only way that this equation can become true is that this term must be 0. Correct? So this term has to be 0, and therefore from that we know that x is equal equal to L over 2 minus S over 2. So this, ladies and gentlemen, I really don't like to speak, with the PowerPoint, but it is what it is. This is where the maximum load will occur, not the maximum load. I mean, this is where the load placement will give you maximum. You need to place your load group such that this distance x here is equal to this. In other words, notice that, okay, some of you are still making notes on YouTube. So if you want to make notes, make it now. I'll give you a minute. I will stop. Or we place the load so that, look at the picture. I'm going to erase something to just clear your mind. This, ladies and gentlemen, is the center line of the beam. We place the load so that this resultant force, the sigma P, and P3 here, the load closest to your sigma P, has the same distance to the center line. In other words, we can say we try to place the center line of the beam right between Q and the load closest to it. Say that again. Let's say P3 is closer to Q than P2. We will try to find the way to place our load so that the center line is right between Q and P3. So with that said, it means that this distance and that distance are equal. That's a trick. Once you know the placement, place the load according to this condition, and you go ahead and try to find maximum moment by using your typical, say, equilibrium stuff. Any questions? Believe me, it's easy. Calculation is easy, and I always think that if you don't study structural analysis, give it to kids, I think they probably can do it because they don't think too much about it. Enjoy trying to place the load to get the maximum moment. But now you this is structural analysis. I can't do this. What is this? Stuff like that. So when you start thinking negatively, that's right. It's the end of everything. Yeah, go ahead. Okay. So is there any question? If we don't have any question, let us try to get to see the example. Okay. Yeah. Oh, now the group of moving load shell moves from right to left on the 50-meter beam. Okay. Calculate maximum positive bending moment is the group will induce in the beam. Also calculate how much shear force at midspan has changed when load number 4 replaces number 3 at midspan. This is probably the bottom line of why we study this, because we need to make use of this in the real design. Okay, so which one you want to do first? The moment or the shear? Okay, good, shear. So here it is. Let us the flip side of the shear at midspan, right? First. All right. So here you go. Now it should come naturally. We talk about midspan and the shear, the influence line of the shear at midspan should look like trying to make it like this. No. Okay, something like that. Okay, and it's a mid span, so we know that the height here it has to be one, right? Change it to here. Right, so therefore this is minus 0.5, that is 0.5. This is the right? I should write the influence line of V and mid span. Okay. Now, ladies and gentlemen, I think that's probably too small. Try to enlarge. See that you can read that, right? Oh. Okay. Remember the increase decrease method? It is the force multiplied by dx multiplied by slope, right? So I don't remember how I tried it. So you see, I will erase this because it gets in the way. Say when load number 4 replace load number 3. So before that begins, we have load number 3 here. Right? And then somewhere load number 4 follows. Because it says here, load when load number 4 replaces load number 3. So 4 will move to replace 3 here. So I'm trying to write everything. And then we have 2 and 1. So this is the beginning. Guys are ready? Maybe. Okay. So when I say load number 4 will replace load number 3, the movement is this. Yeah, right? At the initial point, 3 is at its start, and then 4 will move to replace 3. Yeah, kind of works beautifully, right? This thing. You know, I remember the first time that we had the online class, I didn't even know how to synchronize the iPad. The student taught me. Yeah, seriously. Then, you know, we could be ready to change, adapt to the thing. But the world evolves so quickly now. So here's the beginning. But now is the point where I want to know if this occurs, 3 and 4 like this, how much the shear at mid-span is going to change. So first thing that we know is that in order for 4 to replace 3 at mid-span, it needs to move the entire load needs to move with distance, much distance. Correct? Because 3 and 4 are 13.5 meters apart. So if I say 4 will replace 3 at mid-span, it has to move with the same distance as they are apart. So now 4 is where 3 once was. Because right here, if I write, maybe it should help, 13.5. You see, if I move this, why do I write so confused? The distance that it moved will be 13.5, you see? Wow, it's like making animation. Right? So now we know the delta L. Now, what about the slope? Okay, the slope is, of course, if this is 1, the entire length is 50, so slope is, of course, naturally 1/50. Right? It's 1/50. The beam is 50 meters long. And this height is 1, so the slope is 1/50. Okay, now one thing I do love about being in the classroom is that I can see where you guys are, and I can say control the pace much better. Okay, now take a look at this. When the load moves to the right, you can see everyone is climbing up the slope. Again, this a little bit. This is pronounced climbing, not climbing. Climbing. I remember. Yeah, it's a bad joke, but yeah, let's not put it on the record. You see, everyone is climbing up the slope. Even load number 1 will climb up from the more negative to the less negative value. Number 2 is from more negative to the less negative value. Number 4 is more positive, and number 5 is more positive. So in effect, everyone except load number 3, which we have to keep a bit later, will increase the shear at midspan. Do you agree? And the number of the shear that at midspan that increase by the movement of load number 1, 2, 4, and 5 will be equal to the load themselves. So I can say delta V is equal to load number 1, which is 4. Load number 2 is 15. Load number 4 is 15. Load number 5 is also 15. They move by 13.5 meters. Correct? Because that's what we agree upon, that it's the distance that we need to move the load, or the load has to move in order for load number 4 to replace load number 3 at midspan. It's a distance between them. So that's how much needs to move. And then we have the slope 150. So see how easy that is? That's how much the shear at midspan will increase when load number 1, 2, 4, and 5 move. Are you with me so far? It's not so difficult, right? Just playing a game. Like I and seek. I'll hide your points. You see for it. Right? Okay. Right. So now, what about load number 3? You think? Are you ready? Load number 3. First of all, there are 2 ways to handle it. First, the natural way is that you look at load number 3. It used to give you the positive value by staying at that point. Okay. Now I can try to write load number 3 simply. Maybe it helps. Unacceptable. Okay, better. Now we try to focus on load number 3 alone. Load number 3, before it moves, it gives you the positive value, which is equal to See, I'm trying to write. I never did before the move. So you need to try to read this before the move. This is extra service, you know. Before the move, load number 3 gives you the positive share equal to, okay, can't see it. Better. Load number 3 used to give us the positive share because it used to stay on top. And the value of positive share it gives is equal to the ordinate here, which is 0.5, multiplied by the load itself, which is 15. This is the value that you used to have, correct? Are you still with me? It's like, okay, I used to have 10 baht in my pocket. Now my friend, you know, borrows it, it's gone. So now what I ask you how much money you have. You have 10 baht less because it's gone. So the effect is that the shear force at midspan will reduce with this much because load number 3 used to give you this, but now it's gone. So this is the first effect. We use to positive value this much. So the delta V will change in a negative way because this one, this positive value is now gone. But not only. I'll give you a minute to take notes. But not only that, because not only the 3 that used to give you a positive value and that now that positive value is gone, the 3 now moves into the negative value. Not only that the positive value that it used to give is now gone, it now gives you a negative value as well. So I'll try to write for you after the move. This positive value is now gone. This positive value is now gone. It's like a speaking language. You can take note of yourself. But I was becoming a little bit more concerned that maybe you can't take notes. I'll take note for you. In fact, I don't have to write this. And new negative value is now introduced. Okay. You know what? Let me try to do this. Okay, this is once positive value, and now we have the new negative value. Which is, now we have to do some calculation. Because we know that the distance of the load moves here is 13.5, right? The negative value that is introduced to your shear midspan has to be equal to the load number 3 itself multiplied by its ordinate. We have to calculate the ordinate. Okay? Now this is 13.5. I think that's many of you are writing, so let's wait 30 seconds. We need to calculate the new ordinate. We know that this distance is 13.5, half the span is 25. So this is fine. Can I decline that? Some iPad air would like to share group problem number 6 with you. Once. Okay. All right. So 25 minus 30, how much is that? So that's 11.5, am I right? The distance is not very realistic. Okay, you can draw it, you can write better with you. So that's 10 to 25. The height is 0.5. So the new ordinate is 0.5 multiplied by 11.5 over 25. That's a new height. And then multiply by the load itself, which is 50. My water will okay. So now, as a result, delta V should have these value coming in. First one is the one that we used to have as a positive value, and now it's gone. That's minus, this is 7.5, right? So it used to be positive, now it's gone, so it's minus 7.5, it's gone. Remember that we are calculating the change of the shear force, not the shear itself. So the fact that the positive value is gone gives you the negative change. Correct? Like you have your money reduced by that much. And then another term coming from here. Minus that, because it is now the real negative value that exists when load number 3 moves from positive to the negative region. Now we can have when load number 4 moves to replace load number 3 at midspan, the shear at midspan reduced by 4.335 tons. It reduces. This equation doesn't give you how much it is. It tells you that load by placing load number 3 at midspan, you have shear at midspan more than placing load number 4 at midspan. Correct? Yeah, check that. Really? Bad? 49, right? Multiplied by 13.5. Yeah. this one, second one, because the second one is the value, the positive value that load number 3 used to give when it was at midspan. Now it's gone. So the positive value you used to have is gone. So in terms of the change, it's negative. Think about it. You used to have 10 baht in your wallet. It's now gone. So I'm asking you how much money has changed in your wallet. So you say minus 10. Because your money in your wallet reduced by 10 baht. The same thing. You used to have a positive share equal to 7.5. It's now gone. So the change of share is minus 7.5. The change, you remember, I keep saying this, we are calculating the delta, not the share itself. We're calculating the change of share, not the share itself. And this, sorry, we need to fix this too. So that would be 2.28, right? You don't help me. So sorry, we need to change our conclusion. Now, when the load number 4 moves to replace load number 3 at midspan, the shear at midspan now increases by 2.28 tons. We don't know how much it is, but we know that the change of the load placement gives you an increase in shear. We can say placing load number 4 at midspan gives us shear at midspan more than placing load at midspan. This is what the method tells you. Question. Crystal. Okay. Very crystal. Uh-huh. Now, okay, I forgot. This is just the first one, right? And we start like at 35, so I think I can have 10 minutes more. So let's say the second approach, somehow some of you will like the first one better, some of you will like the second one better. Okay. The question is, are you ready? Yeah. What? That's wrong. Right. So, is some of your friends still writing something? So I'll wait. You know, instructing or giving a lecture for 3 hours doesn't equal to working 3 hours. It's much more tiring. But maybe it's just me, because I can't act like a normal person. Somehow. As if it would help the content get into you more. Like trying to stop it, choose the road, things like that. Anyway, we are ready. I hope. See your friend start drawing flower now. Let us go back and look at this movie. Are you ready? Yeah. Okay. Let's do it. Now let us go back here again. You know, we all know by now that load number 1, 2, 4, and 5, they will give you the same result. The problem is always with load number 3, because there is a change in the nature of the the shear that it gives from positive to negative, so on and so. But the easier way that we can look at load number 3 is that you can say load number 3 goes up the slope as well by the same distance. Okay, so let me write it. I have a love-hate relationship with the straight line option. Okay. Load number 3. Why like so close? Load number 3, you can say it goes up the slope, just like the reservoir. So you can say, okay, my load number 3, which is 15, moves with the distance equal to how much? 13.5. And the slope is 150. So now I move my load number 3 here. Up in the sky, but it can't stay there because it's empty air. So it has to fall down here. So the change here from here to here, it just simply, sorry, it's pretty ugly. Parentheses doesn't cover everything. The change here is equal to the load itself. Which is hopefully 50, yeah, minus 1. Because this is 1, right? Now, whichever you like more, you can use it. Because it should give you the same result. This is very convenient, if you ask me. Because now you put every load, multiply by the distance it moves, and the slope, and then, okay, bring it all down here by the extra term. But I need to show you the first method because it is, say, the engineering explanation to how things happen. This is more like giving you a shortcut formula without giving you the opportunity to understand what is going on. Okay? Any questions? Should give you the same result. So in the end, you can write the change in shear is just the every load, right? Okay. 4 plus 15 plus 15 plus 15. Oh no. Look at my hand. Hey, what to do that? 15 plus 15. Everyone travels with that distance, multiply by the slope, and then minus 15. Hopefully, we should get the same number. Oh yeah. Okay. 2.28, right? Yeah. You should try to write the summary so that your understanding is polished. Okay, and make sure that you understand it. Okay. Yeah. Do anything you like. And I never asked you to show me how you do your calculations, right? But if it's wrong and there's no trace, you know what happens. So you do it, you can do whatever you like, whatever you like. and I'll do what I like as well. Right? Fair enough. Yeah. No, the thing is this. I now I have found that the first time that the rubric things and how I grade the problems was introduced, it helped students. But I think not all of you look at how things are graded. And with that, in public, you know it, you see it. I create it and I use it for grading. Grading is fair, and you can always check with that. And I'm a human being. From time to time, I can make mistakes, and you can always make a protest if you don't agree by grading. Okay. Yeah. And we share the platform of grading, so everything is done fair as well. You ask me. Okay, guys. Any questions? Now we have the moment. One last business left to take care of. Okay, guys. Let's stop the record.